So, where were we? Last time, let's make that a little bit bigger. Last time, we were talking about relations for a couple of days. And today, we are starting a new topic, which is graph theory. And indeed, the last topic of the summer. How exciting. And it's a good one to end on, I think, because graphs are very fun to play with. They are also have an incredible number of applications. And also, we've even seen it a couple times already in this course when we were talking about binary trees and when we were talking about Ramsey numbers. So finally, let's come back and treat it correctly. So a graph, let's call it G, is a set of vertices and a set of edges. So G consists of a set of vertices. These are the dots or nodes in our graph. And a set of edges. And the edges, each edge connects two vertices. Which we call its endpoints. So let's start right out with just giving a bunch of examples. So the complete graph which is denoted Kn. So the complete graph on n vertices is the graph with all of the edges that you could possibly draw. So, and there's one for each n, for each number of vertices. So K1 is a single vertex and no other vertices to connect it to, so that's all it is. K2 is two vertices and they are connected by a single edge. K3 is three vertices connected each both to the other two. K4 is four vertices with all of the possible connections, and so on. Maybe I'll even draw K5. There you go. A little pentagram. And so on. So this is one big class of examples. Another useful class of examples are n cycles. So the n cycle graph, which is denoted Cn, is n vertices in a cycle or a ring. So let's start it from 3, because with less than 3 vertices, you can't really make a ring. So C3 is a triangle, so it's the same as K3, in fact. C4 is 4 vertices connected in a ring, so it's a square or a rectangle. C5 is a pentagon, C6 is a hexagon, and etc. Another big class of examples. So yet another one, the n cube is slightly more complicated. So it's the graph with 2 to the n vertices Or maybe let me say, you kind of know what an n-cube is, probably on some level, but here's one way of writing it down precisely what the graph structure is. So it's the graph with 2 to the n vertices corresponding to bit strings. So remember that a bit string means a string of 1s and 0s. So each vertex corresponds to a bit string of length n. That's why there's 2 to the n vertices, because there's 2 to the n of those things. You will know from our discussions of counting. So each vertex corresponds to a bit string of length n. And edges are drawn to connect vertices that differ in exactly one position. Which is to say that their bit strings are the same except for exactly one spot. So the 1 cube has 2 vertices corresponding to the bit strings of length 1, and they differ in exactly one spot, so they are connected by an edge. And just to move back to these ones, this happens to be K2. The 2 cube, so it has 4 vertices corresponding to the 4 bit strings of length 2. So I'll label these 0, 0, 1, 0, 0, 1, and 1, 1. And then we draw an edge where 2 of these vertices differ in exactly 1 bit. So for example, these 2 differ exactly in the first bit, so we draw that edge. These 2 differ in the second bit. Again, these 2 differ in the second bit, and these 2 differ in the first bit. But these 2, for example, both of the bits are different, so we don't draw that edge. And same with the other diagonal. So this is the full 2 cube, which happens to be the 4 cycle. Then the 3 cube, let's draw this also. This now has 8 vertices. So let's, and maybe you're seeing sort of why this corresponds to a cube. Because you can think of these bit strings as giving you the coordinates of a point in space, and saying that they differ by in exactly one position is saying that you can get from one point to the next by traveling along one of the coordinate axes. So those are the edges that you draw on the cube. So 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. And let me not go through it in detail. You can check for yourself if you want, but they are connected in what you will recognize as a familiar regular cube. Very good. So here is already a nice big store of examples for you to draw from when you're thinking about graphs. But of course, you should always be experimenting and drawing your own examples. There are many, many more examples than these. So now let's go over a couple of different, slightly different settings we can consider. So these examples that we've given so far, they are all finite, simple, undirected graphs. So I've thrown on a lot of modifiers there. So let me explain what all of them mean. So your graph can have infinitely many vertices, in which case it is an infinite graph. But we basically won't consider this case at all for this course, so I'm going to skip right over that immediately. Some things that we might have occasion to consider are you can also consider graphs with multiple edges. So, for example, this is a simple graph, but you can draw double edges or even triple edges between some of these vertices. That's what we mean by multiple edges. Or you can draw loops, where a loop is an edge that starts and ends at the same vertex, like that. So a graph that does not have these things is called simple. That's what this word means. So a graph with no multiple edges or loops is called simple. And that's the case in all these examples we've seen so far. They have no loops and no double edges. And finally, another different class of graphs that you consider are directed graphs. So a directed graph basically is what it sounds like, has a direction associated to each edge. As opposed to the examples we've talked about so far, do not, and are called undirected graphs. So an example of a directed graph just means that you give a little arrow on each of the edges to indicate that this edge goes in a particular direction. So instead of an edge having two endpoints that are basically on an equal footing, it has an initial vertex and a terminal vertex. So the edges are distinguished, or the endpoints are distinguished. And you might also have a situation where you have multiple edges, but now they can be going in different directions. So there's that added layer of complexity as well. But in general, let me say, for our purposes, graph will mean what we said before, finite, simple, undirected graph. And basically we will explicitly say if we ever want to deal with any of these additional possibilities of possibly having multiple edges or loops or giving directions to our edges.